So, switching gears a little bit, I'm going to present the main work that's here, so modeling of frame structures in fire using OpenSees. And before I start, I have to first acknowledge a lot of work that has been and still being done by a research group in Edinburgh. Professor Usmani, he's been the main developer of what's now starting to be available in OpenSees to model fire. And I also have to acknowledge two other people. One is Ruben, and Ruben has really been doing most of the work that I'll be showing here in terms of validation and also verification of code that we've been doing. And a colleague of mine, that's his co-advisor, that's Ruben's co-advisor, Luis. So, very quickly, I'll give you a quick background and for those of you like me that until about a year ago, I had not really done anything related to fire. So I'll talk to you a little bit about what thermal actions and what thermal mechanical materials properties are useful, mainly looking at steel and concrete. Then go into a few application examples and talk to you a little bit about ongoing future work before we go to some conclusions. And the first main thing that I have to say, and that you may have an intuition about, is that materials degrade at elevated temperatures, right? And so that's the main idea behind everything that you've been seeing here. And so how can we actually model this degradation at elevated temperatures? That's what we've been trying to look at in OpenSees. There's a lot of work, and there's fire engineers, and there's structural fire engineers. I'm starting to be more of the structural fire engineer. But traditionally, fire engineering has been very prescriptive. So it's prescriptive codes, and typically you get things like structural members need to be protected, and so they tell you what an acceptable maximum temperature is, and they'll tell you what's the fire duration. So for how long does that temperature have to be sustained? And then things as simple as the steel members need to be protected, and they have to be protected. And then reinforced concrete members, typically the cover, and all you have to work with is what's the cover that you need to provide, such that through the reinforcing steel, such that you have your good design. But if we do want to start looking at performance-based structural fire engineering, then we can start talking again about life safety. And that typically has to do with evacuation of people, traditionally the people that are going to put out the fire. And so that's what we're starting to look at, is actually estimating the performance of members and of structures related to fire. And why are we doing all this? Is because we want to start looking much more at multiple hazards or cascading hazards. So if there's an earthquake and then there are fires, if you have a problem of fire following earthquake, you'd like to have one tool where you'd be able to do both. First do earthquake analysis, and then do your fire analysis. And OpenSees starts being an example of a tool where you can use that. And then we're also starting to think about it, to look at what if you have an explosion and then you follow by fire, and looking at what could be done by explosions, example of what Michael showed you today for water, for tsunami, but same ideas can be used for impact and fire. Okay? Very, very quickly, and this is my one or two slides on what we're looking at in terms of the thermal actions. And so there's, fire is a complex phenomenon, and to actually be able to model it, it's very complex. But typically you have, for a fire, there's three things that you have to look at. You have to look at the fire, if there's an actual ignition, and if there's going to be oxygen to actually provide to the fire for it to grow. And, more or less, can we see here? So very, very briefly, this would be what your temperature versus time would look like for a fire. So you have a very initial stage where you have an ignition, and then you have an initial phase where things are starting to heat up, but you may not actually have this thing which is called a flashover. And a flashover is when you actually have, after that, you have a fully developed fire where your structural elements may now start being affected by your fire. And once you reach a peak temperature, then you may have cooling, okay? So this is what a real fire curve may look like. typically in design and even in analysis, so already looking at a fully developed fire, for us as structural engineers, we don't really care if the fire doesn't really pick up and affect your structure. So we're looking at fully developed fires. You may have a nominal time temperature curves. An example are the ISO 834. There's a similar curve, nominal time temperature curve, which is an ASTM 119 curve. And then if you have a little bit more information of what you're trying to model, you may come up with parametric fire curves, which may be controlled by ventilation or controlled by fuel. And you see they may have already the effect of the cooling, which you don't have in a nominal time temperature curve. Or you can go to full-blown computational fluid dynamics, which are very, very complex. And for most cases, they're not. There are some codes available, but it's not very effective to design or even to performance-based analysis. That's where we're going to go with computational fluid dynamics. Very quickly, I'm going to be talking mainly about the European experience. So I usually use ISO 834 curves, but they're very similar to the ASTM curves. And here's an example and a comparison between the two curves, just for you to have an idea of the differences. But in terms of time versus temperature, it's more or less the same. All of the work that I'm going to show could not be done right now if we didn't have this initial work done in OpenSees. So right now there are classes in OpenSees for heat transfer. So that's how you actually prescribe your fire, how you're going to transfer the heat to your structural elements. And then you also have the boundary conditions. So for example, here is where you have your fire model, and you can have the nominal or your parametric fire that I just talked about. You can define those as a time series and then apply it as a boundary value problem. A boundary pattern, boundary condition to your element. So that's what has been done already, mainly for steel and concrete in OpenSees, and for just a few material models. There's lots of work that can be done now to extend for many of the capabilities of the material models that are in OpenSees. But right now, there are some important properties that I'm putting up here just for you to have an idea and to come back and look at. So thermal conductivity of concrete and of steel on the left and concrete here on the bottom. Here you see this is interesting, a specific heat of concrete with the temperature, and as a function of the moisture content in the concrete, you have very different behavior as the temperature starts increasing. And thermal conductivity also, different behavior depending on what type of concrete you have. Okay? So if you look just at the very simple case of thermal elongation, this is the typical behavior for steel here in dark, and for concrete it's typically a curve like this. The concrete depends, and the curve for the concrete depends on what type of aggregates you have. So you have to be careful in terms of, are you really modeling your structure if you want to do a performance-based assessment? But steel, this is the typical behavior. And then steel material degrades. So it degrades at elevated temperatures. And you see here are three curves that are theta factor of reduction. You start with 1, with your initial strength or stiffness. And then as the temperature increases, you start slowly going down to having, for example, if you look at the yield force, you start up to about, let's say, 400 degrees Celsius. You don't have any loss in terms of effective yield strength, but then very quickly you start reducing your effective yield stress. And that's important to note because there are going to be things like localization that you typically only worry about softening materials, right? So in steel typically hardens. You don't worry so much about steel and localization. But now in fire, you are going to have softening, right, in your steel material. And so you also have to start worrying again about problems of localization later on. And we heard a little bit about localization today. That's why I brought it up. Here are two examples of curves for concrete. If you have siliceous aggregates or calcareous aggregates, you see that the reduction in terms of your capacity here is the characteristic strength of concrete, something more used in the Eurocode, would be similar to your FC prime and to the FC prime we use here in the US. And then you have, as a function of temperature, you see that your capacity goes down. This is one example. Right now, only this curve 1 is implemented in OpenSees. So if you're in an area where you have mainly calcareous aggregates for your concrete, then you need to implement the next one. Okay. So, and at the material level, I have the next slide where I'll show more of what materials right now are implemented. But you may have used Steel 01 if you used OpenSees. Now there's a new Steel 01 thermal that includes the stress strain and also a variable for the temperature. So as temperature increases, how does the model vary? Steel 02, Concrete 02 thermal. So there's already a few, but many, many more material models that you may want to use as an earthquake or a structural engineer doing earthquake analysis are still not implemented and need to be implemented. So here are a list of the current elements, section, and materials that are already implemented. And the results that I'm going to be showing you next in the validation are using the displacement beam column thermal and using Steel 01 and the elastic material. Just to keep, in the interest of time, I'm not showing anything related to concrete. So, very, very simple examples, and just to show you how easy it is now to use this fire component, let's look at a simply supported beam under thermal elongation. So at the left, I have a pin, and here at the right, I have a roller. And along the cross-section of a bar that's 0.1 by 0.1, we're going to apply the top fiber at the bottom fiber, and throughout the section, the same temperature of 1000 degrees Celsius. So we're going to start increasing that temperature until we reach 1000 degrees Celsius. And we are going to use Steel 01 thermal. And in terms of creating your code, your OpenSees code is basically the same. So for those that have used OpenSees, you recognize all the commands. So you have your model builder, then you create your nodes, then you can do your fixity, so whatever restraints you have. And then for this truss element that I'm going to use the displacement beam element, I'm going to use uniaxial Steel 01 thermal, and you provide the Young's modulus, the yield strength, the Young's modulus, and the strain hardening at the end there. Then you can, for example, very, very simple case. Here we're analyzing, we can compute and develop a fiber section. Here I'm discretizing this cross section, which is 0.1 by 0.1, just into two fibers in the cross section. So just to show what kind of results we can get. And on the right you have what you're implementing, and for the fiber thermal you can use patches, you can use fibers, so you can find something like this. This is just for you to have as a reference when you try to use it and replicate this example. And then as you move forward developing your model, you need to construct your geometric transformation. We're going to use linear. Just for this very simple case, I'm using linear because this is a thermal elongation problem. And then your displacement beam column thermal, and you have initial element ID, initial node, end node, number of integration points. This is a displacement beam column thermal. So we heard Vesna today showing that if you use 3, if you want to reduce, if you want to use more elements, that's fine, but typically 3 is a good number to use for the displacement beam column element. And section tag and transformation tag. Okay, I have given all the code and what it represents in this example. And then you have to apply your load, so you have a thermal load that you're applying. In this case, it's a pattern, and we're specifying at the top fiber and at the bottom fiber, so what your gradient is. Okay, this is constant along the height of the section. You can also provide linear, or you can, so this what it does, just does interpolation. If you provide only 2 points, it just does the interpolation between these 2 points, so you can have something which is linear. Or if you want something else, you can provide up to 9 points right now in terms of your temperature gradient. So in the end, this is all the code that you need. You have also to provide the analysis at your analysis block. But this is the code that you need to run this very simple example. And for this very simple example, you're going to have your thermal elongation. And so this is what I call here your horizontal displacement versus temperature. And you get exactly, you should just very simple analytical solution as you increase the temperature. And you see that OpenSees is capturing exactly the same response. Okay? So very, very simple, but shows you, if you want to try yourself, very simple code, get your hands on developing this, and then you can actually match it to analytical solutions. I will be providing later to Frank the code for all of these examples, so later on you can download. But right now for the next set of examples, all I'm showing is just what was modeled and what the response looks like. So for the second model, looking at the effect of restraint. So if you have a restrained beam, restraint here at the end, and you're applying a temperature just in this element on the left and no temperature on the element on the right. And as you start increasing your temperature, we're going to be tracking just the displacement at this middle point. We also have an analytical solution, and for this shows you that OpenSees captures very well the response in terms of the displacement versus temperature. I had started to talk about something that will happen, which is you may start having localization of your results, and this already shows that you have softening here, right? So as you start having more and more elements, again, even if just for steel, you have to worry about localization for your elements. This is a nice example just to show if you have an unrestrained problem, but if you look at linear geometry versus nonlinear geometry. But now instead of looking at the axial response, we're going to look, we're still going to look at the axial response, but now we have an initial load which is perpendicular to the beam. So we have a gravity load, a uniform distributed load that's down, applied on the beam, and then we have a horizontal thermal elongation. Okay? Section now is 0.1 by 0.2 meters. The material is still 0.1, and these are the properties that are assigned for the material. Note that E naught here has two meanings. It's not only the initial Young's modulus, but it's the initial Young's modulus at 20 degrees Celsius that we're specifying for the material property. Okay? And it's nice to show, so for the steel, for the section, you have the unrestrained linear geometry response, that's here in gray. So it keeps growing and then basically follows the steel material model. But if you look at the nonlinear geometry, what happens now, you have this load which is applied on the structure. So you have an initial deformation in the beam just due to the uniform distributed load that's applied. And as you start increasing your temperature, you actually start seeing something that first the beam elongates initially, right? So as you're increasing the temperature, you're actually getting that elongation. But due to the nonlinear geometry, what you start getting is that at a certain point, you actually start coming down, and this point actually switches over to the left even as you're applying your thermal elongation. And this has to do with the with the nonlinear geometry, and also because of your nonlinear material that you're using. But this is mainly the effect of the nonlinear geometry. So what if we then go and apply different sets of constraints at the end, so or restraints? We have the unrestrained case, and we have the laterally restrained cases. And I'm looking at linear geometry, nonlinear geometry for both. And now instead of looking at the horizontal displacement at that tip, we're going to look at the vertical displacement in the middle, because so we can compare the lateral restraint to the unrestrained case. Okay? And you see that in terms of the vertical displacement, if we work with linear geometry and nonlinear geometry, but for the unrestrained case and the laterally restrained case with linear geometry, they follow more or less the same vertical response. But from the beginning, if you start with your nonlinear geometry of your laterally restrained case, which is this one, you have a very, very different response in your analysis. These nonlinear geometries are modeled using the co-rotational, so whatever is right now in OpenSees. And this to make the point that if you're actually going to do any analysis in related to fire, from the beginning, don't think about linear geometry, okay? Start with nonlinear geometry is the main lesson from this. And again, just because we are, or I am an academic, I went to look for this case, what happens to this horizontal reaction? We know we have a uniform distributed load of 20 times 6, so it's 120. The vertical reactions, those remain unchanged. Just by equilibrium, the vertical reactions remain unchanged. But it's interesting to look at this horizontal reaction, and you see as you start increasing the temperature, what happens as you start increasing the temperature, you're restraining that horizontal movement. The beam wants to elongate, but it can't. So you have a negative reaction. But this, at a certain point, it actually changes. And there's actually a point here at the end, about 920, 930 degrees Celsius, where you actually start having a positive reaction, right? So it's that point when the structure would tend to go back also. Looking at specific sets of constraints for now, also for the rotation and horizontal. So starting to move more and more into what would be a realistic boundary conditions for your beams. Have an initial uniform distributed load that's down, and going to apply now a gradient of temperature. So the top fiber is not going to change its temperature, and we're just going to change the temperature at the bottom fiber. And for a specific set of k theta kh, this here is showing the deformed shape as we increase the temperature. Okay, now since we have this gradient, so here is 0 degrees Celsius on top and 1000 at the bottom, that would be at the when our pseudo load reaches a lambda of 1. So that would be the case where we have 0 here and 1000 at the end. That would be our last deformation that we would get. If we have a pseudo load of 0.2, for example, that means we're applying only 20% of what's here. So we have 0 on top and 200 on the bottom. Okay? So this lambda is the pseudo load or the pseudo time in the analysis. And if we start looking at how your results change with increasing number of elements, you start seeing things where your response starts converging, but you have to be careful again here in terms of what we're calling convergence. We're having the response globally reaching the same response. And here, I'll show you in more detail. I'm showing first the horizontal displacement. So at this end here, the horizontal displacement, you see it's essentially the same up until this pseudo load of about 0.5, 0.54. And then after that load, if you have 2 elements versus 4 versus 6, you see how the response changes with the pseudo time. So again, at the end, I've applied 0 degrees Celsius on top and 1000 on the bottom. And so this is how your response changes. Between 8, 10, and 12, here the response is basically the same. We also see that for the vertical displacement, where initially you have very little displacement, and then as long as you're using the co-rotational, you start capturing very well this sagging on your beam. And this, for example, at the level of the end rotation at this end, also you see convergence of the responses. Okay? Displacement being column element, and so that's what you start getting. How am I doing with time?
Fabulous.
Okay. So example 5. This is another another example where we start very, very simple frame, and all of these is really just to show the capabilities of OpenSees, and then you can develop what you want. But it's also, we've been using these as validation of the code. And so, for example, this very simple case, we have a frame. We're applying a uniform distributed load on the beam up here. And then we're also applying what would be a fire load as specified by the code for about 200 degrees Celsius. So you see that there's a ratio between the delta T applied in the beam and the delta T applied to the column. As the fire develops, this ratio in reality actually changes, right? So for example, if we have 1000 degrees Celsius here at the end of your simulation, in real life, maybe the columns would be experiencing about 900 degrees Celsius. So this is a very academic example, just to show what can be done. But whenever you start using these things, take it with a pinch of salt, and don't just say, oh, we saw that it's always 1.63, the ratio applied to the beams and the columns. Like Professor Arduino said this morning, Pedro was saying, you have to know what you're doing, and I'm starting to know what I'm doing, but I've been reading up for about a year and a half on fire. Okay? And here I have the results where you see they're amplified by 5. So this doesn't actually go all the way down, but it's pretty large displacements. And the results for different lambdas, so different pseudo time, pseudo load that we're using to define the temperature. So the temperature in the beams and the columns are increasing with the same constant lambda. And here it's interesting again that as you increase the beam temperature, you start getting the response for, let's see, at 0.76, your beam was actually elongating, so it's longer. It started in the black, and now we're out here in the yellow at 0.76. But then after a while, after this point of 0.76, it actually changes, and everything starts going back in, right? So your beam starts going down a lot. It brings these 2 points. This point brings it inward, and this one also inward. Okay, so it's realistic in terms of what's actually being caught in the analysis. And this one is more of academic interest again. This is following the axial strain, so we have a fiber section, and for the steel, and it's actually this cross section, which is modeled using 14 fibers along the height. And here I'm reporting just the axial strain, and what I'm calling this axial strain is the axial strain of the cross section and the curvature of the cross section. And you can see that you can track. We start initially. We have, where are we? So initially we're here, and then as we start doing our analysis, you see that different sections have very, very different response in this analysis, and I think this is just interesting to track as we do the analysis. So initially, you have here you have a positive bending moment due to the uniformly distributed load applied to the beam, right? So that's your initial moment that you have there. And then as you go during the analysis, the moment goes up and down. Your axial load also varies, and initially your beam was in compression. It's trying to grow, and it can't. So initially it's in compression, and then at the end of the analysis, it's in tension, even at that middle fiber. Okay. So again, looking at mesh convergence, and I'll here the results are not very visible, but I'd like to point out that you do get some effects of what can be called localization, but more than that, when you start initially with few elements, you can't really, we couldn't initially even pass this stage, so there was convergence problems with fewer elements. And it has to do with the fiber, but it also has to do with the co-rotation, with the geometry that you're trying to capture. And only with increasing the number of elements, we actually see that also only after 8 elements, we're actually being able to get convergence and having this analysis go on until the end. I'll just skip these, and here it's important to note, and very locally you don't get exactly the same response, even as you increase many numbers. But now, if you use 22 elements in both the columns and the beams, you're really concentrating your nonlinearities. In this region, you're concentrating them in 2 or 3 specific, very specific parts of the structure, and so that's where you may have localization problems. So, just like in reinforced concrete, or any problem where you're using softening, if you look at what the plastic hinge length is in your structure, this is a steel structure, but based on many tests, you can go and check what is the plastic hinge length that you're expecting to have in your structure. You can impose that, and that will give you your element length and the discretization that you should use to get good results. With temperature, it's a little bit tricky because, well, in concrete, the plastic hinge also grows as you're doing your analysis, right? Initially, you don't have a plastic hinge, and then it starts developing, and your plastic hinge grows. In steel, with the fire, and we saw there, we have the axial effects, and the plastic hinge also changes length as you increase your temperature. And so you have to come up with a reasonable value for your plastic hinge, and then work with that. I really like this plot, especially because I've been looking for a long time at OpenSees just as an earthquake engineer. And so I would be looking, let's say, at a temperature of 0 or at 20 degrees Celsius. And this would be the response that you would see, or one of these lines would be the response that you would get for steel 0,1. The response, I mean the stress-strain response that you'd see for steel 0,1. So you have an initial elastic branch, and then you have the branch which is B times your initial with the hardening, right? Now, with fire, or with temperature, at elevated temperatures, we're going to have a third variable that's going to be here. And so you start seeing very clearly here how your model changes. So what's in black now is what your OpenSees is, what's imposed in OpenSees. And you see that as you increase the temperature, this point here gives you the yield strength. And the yield strength is reducing, right? You don't see it as much in the Young's models, but you see very clearly that the capacity or your yield strength is reducing. This plot, I need to explain it a little bit better, and as I learn more also, I'll be showing you more of these. But here you see all of the fibers. We have 14 fibers, but I think it's clear to see that the response in the fibers for the 22 elements in green is quite different than the response at the outermost fibers in yellow. So there is this change, and you're getting this localization of your strains in your. I'm finishing up with ongoing work and work that I'd like to do, and if anybody is interested in funding a student, I'd be more than happy to do more and more of these analyses. Right now we're modeling the steel structure. It's a real test that was done in Cardington in the UK. And they actually had different tests, test 2, 1, 2, 3, and 4. Right now we're only modeling test 1, which is on the floor. They applied, just to this beam, they applied a concentrated fire. So that's the region that we're modeling. So this is just a zoom in where we have secondary joists, we have primary joists, and we have columns. And this is an open area out here. It's a void in the slab. And this is the model that we right now are coming up with. We're modeling the beams, and we have a reinforced concrete section and a steel beam. So we're modeling them using rigid links. And then we have all of our concrete on steel deck. Here's the detailed concrete on steel deck that we're modeling, so as unidirectional fibers along that length. This is ongoing work. We're trying, and the student was trying to finish this just before we came, and even yesterday he was trying to finish. We're almost done, but there'll be more work later. And we would like to test OpenSees and actually model this fire test that was modeled. Here's the fire loading, all the timber that they use for the fire. And we'd like to model this next in OpenSees. And work that I'm already doing now is on timber, so implementing the models for timber. This is a timber building. Here are your timber stairs, so the whole building is a timber building. And for modeling this and including the timber degradation in OpenSees. Wrap up. So basic classes are implemented, basic capabilities are right now available. And I stress the word basic, but it's already very useful to start doing things like I showed you today. But for allowing for modeling structures in Fire. And verification of the code that's in there, it's mostly done. So for Still 01 and for Still 02, those are done. We're helping the group of Professor Usmani just with the verification of the concrete models, but it's basically done too. Then we need to do validations on big structures, examples that we're working on now, just to show people what they can do in terms of analysis. Many other material models that are in OpenSees need to be extended. Right now we have that stress strain just at one temperature. We need to create that model to also account for the temperature for all the other concrete models that are available and that are of interest to everyone, but mainly for concrete and timber. And now I think we can start addressing more complicated problems. So doing performance-based assessment for multiple hazards, right? So I actually started this work because I wanted to do, and I still want to do, and we're going to do fire following earthquake, okay? And we realized, well, there's still a lot that we have to finalize with the fire before we can do fire following earthquake. But earthquake and fire are the next ones. Impact and fire, we'll also combine these nicely. And then, in essence, multiple hazard problems. Okay? Any questions?
Let's take a question.
Thanks.
Can you show me the picture about your timber structure? Is it the 6-story building? Is that a timber structure?
Yeah.
Is it common in UK?
It's not very common in the UK, but yeah, they also tested. It's more common in Sweden, and there was also some funding from Sweden into this group, but it's not very common in the UK.
Okay. And my second question is that when you do analysis, do you somehow incorporate some uncertainty in the temperature or like locations?
No.
Okay.
That's all good things to consider.
Okay.
So sensitivity, things that Professor Joel Conte and Michael Scott talked about doing uncertainty and sensitivity analysis in an automated way. That's a whole lot of work that can be done in OpenSees to extend to also have. So each material model, if you want to do a sensitivity analysis, and you want to do DDM or FFD that they were talking about here, you need to have also that implemented into your material model. So it's another extension.
But in terms of fire, it could be
The loading.
have some loading.
Loading is a big thing, definitely. And I have here just one slide in terms of loading. So I talked about what's a code, what's a prescriptive. So for example, here is a prescriptive, right? This is what would be a prescriptive that you would probably specify in your analysis when you have more information what we're specifying. And for that example, this is what was actually seen in the structure. So the loading is a big thing. But if you know the loading, you can do a good job modeling, but it's always harder to estimate the loading.
Right. Thank you.
Okay, so let's take a 4.5 minute break and come back. The big hand is on the 7.5. And we'll have the next set of topics.
Thank you.